I would like to welcome all of our friends and colleagues at our 3 other sites today. We've got the University Corporation for Atmospheric Research in Boulder, Colorado, the Johnson Space Center in Houston, and the Applied Physics Lab in Laurel, Maryland. NASA's planetary science, it's driven by the questions. How did our solar system form and evolve? Is there life beyond Earth? And what are the hazards to life on Earth? NASA's Discovery and New Frontiers programs are lower-cost planetary science investigations searching for answers to those questions. The missions are revolutionizing perceptions and challenging long-held theories as they return amazing new images, tons and tons of data, and even samples. The missions are all proposed by a principal investigator who works with a large team of other scientists and engineers from around the country and sometimes from around the world. These are all people with lots and lots of questions who are on a quest for new knowledge, and they're looking for innovative new ways to explore. Our missions are exploring the planets, moons, the asteroids and comets with flybys, orbiters, landers, rovers, impactors, and sample returns. Today we'll be considering mission design. You're going to be hearing about some really incredible space missions. Many of you are familiar with them, but do you ever really think about the genius that it takes to really make a NASA space mission fly? I think we often can take it for granted. You hear it on the news, oh, put a spacecraft into orbit around dwarf planet Ceres. Oh, and the traffic's backed up on the 5. It becomes pretty routine, but it really is pretty extraordinary. So thinking about creative mission design, how would you land a rover on Mars? Or send an impactor into the surface of a comet? Or grab samples from the surface of an asteroid to return to Earth? And don't forget about all the constraints, the cost, the mass, and the schedule. New Horizons has the audacity to fly a spacecraft the size of a piano 3 billion miles from Earth to reach tiny Pluto. And after 9 years on that interplanetary highway, it'll get there in July. It's just amazing. So as you work through the design challenge we're going to be presenting to you later on, please think about the science questions that are driving these missions that you're going to be hearing about. And consider the instruments on the spacecraft. How were they chosen and why? I'm going to be going over all of those briefly, and consider it for what we're going to be doing later on. So for the past 5 years, JPL has had a team of visual strategists who merged design thinking with rocket science. This is left field, where creative ideas and mission ideas are born. Left field looks like a preschool with whiteboards. It's packed with sticky notes, bins with Legos, pipe cleaners, and other crafty items, all to help the scientists and engineers brainstorm radical ways of exploring space. The ideas literally come out of left field. There are 3 phrases written on the walls: encourage wild ideas, defer judgment, and build on the ideas of others. It's the napkin sketch stage, where all the different disciplines come together. Compelling science ideas become captivating stories. How can we get into the caves on Mars? A grand scheme may be lurking in a container of Tinker Toys. So speaking of Mars, I'm going to give you a short overview now of the 6 current Discovery and New Frontiers missions, and later on you'll be hearing more from some of the team members on some of the various missions. So InSight will place a geophysical lander on Mars to study its deep interior, giving us insight into the processes that shaped the formation of all the rocky planets in our inner solar system. It's planned for launch a year from now, March of 2016. It'll arrive at Mars 6 months later and spend 2 years doing science operations. So how does a terrestrial planet form? Some of you may have remembered our accretion and differentiation activities that we've done in the past. A planet starts forming through accretion. As it gets bigger, the interior begins to heat up, and then stuff happens. We don't really know what all that stuff is, and that's one of the things that InSight is really looking to help us fill in the gap. And then finally, we end up with the crust, the mantle, and the core. Here are the science objectives of the InSight mission. It's about determining the size, composition, and physical state of the core, thickness and structure of the crust, composition and structure of the mantle, learning about the thermal state of the interior, and determining the current level of tectonic activity, and finding out about the meteorite impact rate. This is the landing area. You can see InSight over to the right in comparison with other NASA missions that have been to Mars. Just this last week, one site has been identified as a really good potential candidate. It's smooth, flat, not rocky, something that a lander might actually be able to land safely on. So these are the science instruments on the InSight mission. One is a seismometer to tell us about those Mars quakes. One will measure the temperature, the heat flow and physical properties probe. And the RISE instrument will detect the wobble and measure the Doppler shift and tell the scientists a lot about the distribution of the internal structures so they can better understand how Mars was built. This is a picture of InSight being built. That thing is called the ARM, and it's used to deploy various things that will be needed once the spacecraft arrives on the surface. It's always kind of fun to see what's going on as it's being built. So OSIRIS-REx, you're going to be learning a lot more about OSIRIS-REx later because you're actually going to be building a model of it. OSIRIS-REx is NASA's first asteroid sample return mission. It's planned for launch next year also in September. In 2019, it'll arrive at asteroid Bennu, where it'll spend a couple of years in orbit, mapping, measuring, finding the ideal place to grab a sample from. And then after it does grab that sample, it will come back to Earth in 2023. These are the science objectives. It's about returning and analyzing the sample, documenting the topography, mineralogy, and chemistry at the site, along with globally mapping all of them for the entire asteroid, measuring orbit deviation caused by non-gravitational forces, and comparing observations made of the asteroid from what have been done on Earth to what they're getting on the spacecraft. These are the instruments. There's a laser altimeter, an X-ray imaging spectrometer, a visible and infrared spectrometer, and the thermal emission spectrometer. And that image shows them installing the spacecraft's propellant tank into the primary structure because OSIRIS-REx is still also being built. And finally, the favorite of the instruments is the TAG-SAM, the touch and go sample acquisition mechanism. After it collects anywhere from 2 ounces to 4 whole pounds of material, the TAG-SAM head will be stored into a sample return capsule that will come back for the journey home to Earth in 2023, and it will land in Utah, the same place as our Stardust and Genesis missions did. So Juno is a Jupiter orbiter, and of course our missions are robotic without humans, but we did send some Lego figures along on the spacecraft. Juno will peer through the clouds to reveal hidden secrets from the formation and early evolution of our entire system, solar system. These secrets are hidden within Jupiter. So Juno is the first solar-powered mission going all the way out to Jupiter. It has 8 science instruments that will conduct gravity, magnetic, and atmospheric investigations, plus the JunoCam for education and public outreach purposes. It launched in August of 2011, and it's now still on its 5-year cruise. It'll arrive in July of next year, and after spending about 1 year in its polar orbit, it'll end probably crashing into the surface of Jupiter after it's told us all about what that surface is. Its elliptical 11-day orbit swings below the radiation belts to minimize radiation exposure because that could really damage all the spacecraft instruments. So Juno's science objectives are about learning about the origin, the interior, the atmosphere, and the magnetosphere, with a special interest in learning about the gorgeous auroras that take place on the surface of Jupiter. Mercury revealed by the amazing MESSENGER mission. It was the first spacecraft to orbit the planet closest to the sun, and it started in March of 2011 for what was intended to be just a 1-year mission. It continues to return fantastic close-up images that continue to generate new questions. This is the best image that we had of Mercury before the Messenger mission. It was from a Mariner flyby. You don't get a lot of information on a quick flyby. After 4 years of orbiting, that's the level of detail we now have on Mercury. Here are some other gorgeous new views. With all the time they've had, they've globally mapped it to amazing levels of detail. And this infographic kind of gives you the picture in numbers. That was done last August to commemorate 10 years in space, 8 billion miles traveled, and you see 255,858 images returned to Earth. Talk about an overachiever. It was only required, its baseline science requirements were to return 2,500 images. So it has exceeded that by just a bit. It's an amazing mission. So the key findings include erosion by sublimation of rock, Mercury's offset magnetic field, water ice on Mercury's North Pole was especially a surprise to many, many people, learning about the internal layers, and of course the complete imaging of Mercury's surface. And those are just touching on some of the major achievements. There are publications out there by the dozens. So Messenger's mission is continuing, but sadly we will soon be saying goodbye to the spacecraft. The team has carried out 12 orbital correction maneuvers that have kept Messenger at a safe distance from the planet. It keeps wanting to get closer, and they keep pushing it out farther. The maneuvers use fuel, however, and now after nearly 11 years since launch, the fuel is in limited supply. So the brilliant engineers on their team hope to do 5 more maneuvers and keep Messenger flying for about another 7 weeks. But it is planned to crash into the surface of Mercury sometime between the end of March and the end of April. So it's been an amazing mission, and I, for one, will miss it dearly because it's been around about as long as I have in this job. And it's got a great team of people and finding amazing discoveries. So Dawn is orbited Vesta for an entire year, and you may have heard yesterday it went into orbit around Ceres to compare these two very large and very different objects in the main asteroid belt. Dawn, you may not realize, is the very first mission to orbit and explore any 2 extraterrestrial destinations. Dawn has accomplished a truly remarkable feat, but their folks make it look very easy. Dawn's science objectives at both Vesta and Ceres: Dawn is acquiring color images, compiling topographic maps, mapping the elemental and mineralogical composition, measuring the gravity field, and searching for moons. Dawn uses ion propulsion, and that is why it is able to orbit and explore 2 bodies. Orbiting even one of the targets with conventional chemical propulsion would have been impossible given NASA's constraints. As I mentioned, there's a lot of constraints. The ion propulsion system uses the term thrusts. It thrusts, and it will be thrusting for over 50,000 hours, or the equivalent of about 5.7 years. So those engines have done an amazing job, and the team has faced some pretty good challenges along the way, so you'll be hearing more about that later. These are Dawn's instruments. The framing camera on the left is the one responsible for most of the amazing, gorgeous images that we see. Dawn wanted to have a few more instruments, but you know what? Budget constraints, they got cut. But it's still done an amazing job, and they found ways around and still are able to get the data that they wanted with the instruments that they have. Creativity goes a long way. So for years, scientists suspected that Vesta experienced enormous impacts that sent pieces of the asteroid soaring through the vastness of space all the way to Earth. Data from Dawn has now confirmed that yes, these meteorites on Earth did in fact come from Vesta, and we have more from Vesta here on Earth than we have from the Moon and Mars combined. And thanks to Dawn, we now have pictures close up that show kind of some of the scars that were left on the surface from all of these impacts. Rhea Silvia is the most prominent surface feature on Vesta. It's believed to be an impact crater that's 314 miles in diameter, and it contains what is probably the largest mountain in the solar system, comparable to Olympus Mons on Mars, twice as high as Mount Everest. This nice image shows Vesta's very rugged topography, showing the depths of elevation using color to do that. And had to show Vesta's cute little snowman. Very fun. And hydrogen on Vesta. Dawn found hydrogen that at one time may have been part of water ice before it boiled off and left behind hydrated minerals, but that was a surprise. People didn't expect to find water or anything resembling the signature of water on an asteroid. So Dawn is the first mission to reach a dwarf planet as of yesterday. And then the mysteries are already appearing. Ceres is already puzzling the scientists. This image was taken 2 weeks ago. It reveals two bright spots near each other in the same basin. They may have a volcano-like origin, but scientists really need better resolution before they'll start to interpret this. So stay tuned. We're just beginning to see this ancient world. Pluto. Can you believe after all this time, we're only 4 months from the close flyby of Pluto by the New Horizons spacecraft? Well, that kind of went off the edge, but the science questions are about learning about the atmosphere and what it's made of, how it behaves. What does the surface of Pluto look like? Are there big geological structures? And how does the solar wind interact with Pluto's atmosphere being so far from the sun? Some of the science questions include mapping, or the science objectives include mapping the surface composition and the temperatures on both Pluto and its largest moon, Charon, characterizing their geology and morphology, searching for an atmosphere around the moon, Charon, searching for rings and more moons. 4 more moons have been found since the mission launch. They've all been found by the Hubble Space Telescope, but New Horizons may find more once it gets close. And then hopefully they will be doing all these similar types of investigations once they get out to explore a Kuiper Belt object for the very first time. So the spacecraft, 2.1 meters. It is so small and it has gone so far. It's kind of amazing. The instruments include the long-range reconnaissance imager. That's the eyes, the eagle eyes of New Horizons. And it's essentially a digital camera with a large telephoto telescope, and it's been fortified to operate in the very cold, hostile environment near Pluto. PEPSI is the Pluto Energetic Particle Spectrometer Science Investigation. Yes, they do have fun with their names. The SWAP is the solar wind around Pluto instrument that will measure interactions of Pluto and the solar wind. REX is the radio science experiment. ALICE is a sensitive ultraviolet imaging spectrometer. And RALPH will make maps that show us what Pluto, its moons, and hopefully other Kuiper Belt objects will look like. And if the names Alice and Ralph sound a little familiar from the Honeymooners, intentional. And finally, Venetia. Her full name is the Venetia Burney Student Dust Counter. And it's the first science instrument designed, built, and flown on a NASA planetary mission by students. And the students are from the University of Colorado at Boulder, one of our sites today. So you'll be hearing more about the instrument and the people behind it. The dust counter detects microscopic dust grains produced by collisions that happen among asteroids, comets, and even Kuiper Belt objects. And they've been measuring it all the way on this long journey. So what do we know about Pluto now? Well, we know a little bit from telescope measurements. The orbit's highly elliptical, highly inclined. It takes it 248 years to orbit the sun. The rotational period is a little over 6 days. It's small. It's got rock and ice and bright surface frosts. It's got bright and dark regions. It's reddish in color. It's got a tenuous variable atmosphere. And it's located in a region of the solar system we didn't even know existed until the 90s. So the best photo that we have now from the Hubble is this thing on the left that you wouldn't really even know what it is, but it's comparing it to the kind of resolution that the mission thinks that they will be returning. And to give you a comparison, here's an image of something in what we have, the best resolution we have of Pluto today. Anyone want to guess what that might be? Mars. But you'd never know it from those images. One more at Pluto current resolution. So expect very dramatic results when we start getting these close-up images. And we should start about 60 days or so before the July encounter, really getting the better images. So there are many opportunities for your students to participate in NASA missions. Each mission literally takes hundreds of people to formulate all of those science questions, to build the machines, design the flight path, develop the software, program the computers, create the graphics and animations, tell the story, and get the mission launched. So it's writers, artists, and animators and graphics people, in addition to all the amazing scientists and engineers. So any student with an interest can find a way. They can find their niche in it. And I just wanted to mention, my colleague Eric Conway has just written a book that was just published in the last couple of weeks that tells you all about how JPL got to Mars. JPL has led the US planetary exploration for the past half century, and most recently the focus has been on Mars, beginning in the 90s with Pathfinder, a discovery mission, and continuing through to the Curiosity rover up there now. JPL has led the way in engineering a rapidly evolving succession of Mars orbiters and landers, including roving robotic vehicles whose successful deployment onto the Martian surface posed some of the most complicated technical problems in spaceflight history. In his new book, Exploration and Engineering, Eric reveals how JPL engineers' creative technological feats led to major Mars exploration breakthroughs. He takes readers into the heart of the lab's problem-solving approach and the management structure, where talented scientists grapple with the technical challenges while also coping with, and not always successfully, funding shortfalls, unrealistic schedules, and manager turmoil. So it's really kind of an inside look. He spent a lot of time with the teams and really gotten a lot of good inside stories. So it's available from Amazon and I'm sure other online booksellers. I was hoping to have a couple copies here today, but we weren't able to connect. But it very much goes along with our theme for today about designing a mission and kind of really an inside look at what goes on behind the scenes. So that's it. You can find out much more on our websites. From our websites, you can find links to all of the missions websites, and all of our missions have social media presence. You can find them on Facebook and Twitter and keep up with them really on a day-to-day presence, nearly, especially with more and more images coming back daily almost from Ceres. And from Pluto. Once Pluto starts sending back its good images, it's going to be a long process to get the downlink because it's so far away, and they're going to spend their efforts really on collecting the images. The majority of the downlinking will take place later. So 16 months after the July close flyby, we will still be getting new pictures back. So even though we will have long since left the Pluto system, it'll be like getting new pictures every day for quite a while. So I want to thank you again for being here, for your attention, and we're going to move into our activity. Okay. Okay, and those of you who are watching on our webinar, we will resume in 1 hour at the 30 after.